So, good morning, everyone. My name is Dario Catalano. I will be chairing this morning session on computational multi-party computation. Our first talk will be on black box construction, black box constant round secure two-party computation with succinct communication, and the talk will be given by Akash Shah. Sorry, I will probably mispronounce all the names, so I apologize in advance with all the speakers about this. So please go ahead.
Yes, thank you for the introduction. So today I'll present our black box constant round secure 2PC construction with succinct communication. This is a joint work with Michele, Ankit, Rafi. So let me first begin with a recap on fully homomorphic encryption scheme. So FHE allows computation of both addition and multiplication gates on ciphertext without the need to decrypt it. Now, the main advantage of FHE is that the communication is succinct because one party only needs to encrypt its input and send it to the other party. The other party can then locally compute on this encrypted input any function and obtain the encrypted output. The main limitation of FHE is its computation. Computation is a major bottleneck, and FHE is still slow, and as a result, it cannot be applicable for many large-scale applications. So the next question is, can we accelerate FHE computation using hardware? Well, there has been effort by DARPA with the introduction of the DeepRive program in 2020. DARPA is striving to construct an FHE accelerator that would make it orders of magnitude faster than current software-based solutions. In this effort, Intel and Duality has also joined DARPA in order to come up with an FHE accelerator that can make it orders of magnitude faster. Now, let us see how FHE can be used to construct a secure protocol. So what Alice does is that it creates an FHE public key, encrypts her input, and sends both the public key and the encrypted input to Bob. Bob then performs the prescribed computation using hardware calls to FHE and sends the encrypted output to Alice. Finally, Alice decrypts and gets the output. Now, the main question of this paper is, how do we make this approach maliciously secure? The main challenge is that we cannot make use of zero-knowledge solutions because in order to prove that the FHE computation has been done correctly, because it will kill the purpose of FHE accelerator. So whatever efficiency gains you had through FHE acceleration, you would through hardware, we would simply lose it. Because this would require to prove in software that the hardware computation has been done correctly. So now, the next question is, how can we rely on the efficiencies of hardware-based FHE and get a maliciously secure protocol? So the goal of this paper is to construct a fully malicious security with abort protocol, even if adversary ignores the hardware and uses their own code. So we want to rely on black box use of FHE without the need to explain how it works. And we want to make use of information theoretic tools so that we do not sacrifice the efficiency of hardware FHE. So now, more formally, we consider the problem of two-party computation. Here you have Alice and Bob. Alice holds the input x1 and Bob holds input x2. And parties want to jointly compute a function f on these inputs. And adversary corrupts one of the parties. So in this slide, let us assume that Bob is corrupted. The correctness requirement is that if both the parties are honest, then the protocol should indeed give the correct output. And the security requirement is that if A corrupts Bob, then it should learn no information about x1 apart from what can be inferred from the output of the protocol. So in this work, as mentioned earlier, we consider the setting of malicious secure protocol with abort. Now, in more detail, these are the goals of our work. We want to come up with a protocol which has constant rounds of communication, and it anchors communication that is polylog in the size of the function, so that we want a protocol that has succinct communication. And finally, we want to make black box use of all cryptographic primitives. Well, there are works in literature which satisfy at most two of these goals. For instance, there are constant round succinct communication protocol that make use of fully homomorphic encryption, function encryption, or homomorphic secret sharing, but they do not make black box use of primitives. And there are other works that are black box and constant rounds, but then they are not succinct. So we are the first to construct a protocol in the malicious setting that satisfies all the three goals simultaneously. So now let me describe the construction that we began with as a motivation earlier by giving a pictorial representation of it. So here, Alice samples a public secret key pair and encrypts its input x1 and sends the encrypted input and public key to Bob. Bob is then going to encrypt its input x2, and then it's going to homomorphically evaluate function f on the two ciphertexts that encrypt the inputs. And once the computation has been done, it sends the output ciphertext to Alice. Alice can then decrypt the output and send the decrypted output back to Bob. So this is fine in a semi-honest setting. But now let us see what are the pitfalls we face when we try to extend this protocol in the malicious setting. So now let us assume that Bob is the one that is corrupted. So in this case, what Bob can do is that it can evaluate an arbitrary function that is not equal to f. So then, as discussed earlier, the standard approach is to just use zero-knowledge proofs. But unfortunately, this is not good for us because it would make non-black box use of FHE. And moreover, we would also require that the size of the zero-knowledge proof is sublinear in n, so that we satisfy our goal of succinct communication. OK, so now let's consider the other case in which Alice is the one that is corrupt. So what Alice can do is that it can generate public key and ciphertext of its input in such a way that the output ciphertext can reveal the output of Bob. This can be easily handled by making use of FHE constructions that are robust against such attacks. And indeed, there is such a robust FHE scheme that only makes black box calls to a standard FHE scheme. The second issue that we face when Alice is corrupt is that when we try to simulate the proof, when we try to construct a simulator for Alice, it's difficult to extract the input of x1. So in the next slide, I'll describe how we modify this protocol so that we can extract the effective input with which Alice has participated in this two-party computation. Finally, the third attack that a malicious Alice can launch is that it can simply send an arbitrary y, which is not what it had obtained from Bob as output. And this can be easily handled by making use of a compiler that was given by Ishai, Kushilevitz, and Paskin that makes use of information theoretic max and in their Crypto 10 result. OK. So now let us consider the first issue that I'm going to present in this talk. That is the inability to extract x1, that is the input of Alice. So at a high level, what you make use of is that we make use of verifiable secret sharing scheme and the cut and choose trick. x1, it's going to generate a verifiable secret sharing of its input and obtain this n shares. And it's going to encrypt each of these shares such that the second share is encrypted with R2. Similarly, the ith share is encrypted with using randomness Ri. And then it is going to commit to this shares randomness pairs and give this commitments and the ciphertext to Bob. Now what Bob does is that it is going to use the cut and choose trick. That is, it is going to open a subset of these views that has been committed. Then it's going to perform the following verification checks. It first checks whether the VSS shares are consistent, the open VSS shares are consistent. The second thing that it does is that it checks whether the commitments are consistent. And finally, it checks whether the ciphertext have been correctly computed. That is, for instance, here it will check that the second ciphertext takes as input x12, and it makes use of randomness R2. Now, once all these checks have been done, it's going to make use of all the ciphertext C1 to Cn, and under FHE, it's going to reconstruct the secret that underlies in this VSS secret shares. And it obtains the effective ciphertext that encrypts the effective input of Alice. So now, in our proof, how do we simulate it? What we do is that we simply rewind the corrupt Alice again and again, such that we have learned sufficiently many VSS shares. And then we can simply reconstruct the VSS share This works. The reason is because of the consistency checks that Bob has performed. Bob will, since Bob performs this consistency checks, we can assure ourselves that there are sufficiently many VSS shares that are consistent with each other, and then we appeal to the VSS commitment and or robustness property to argue that we are able to extract a unique effective input x1 in the simulation. Now, there are some other subtleties, that is, what if any of this ciphertext is ill-formed? Unfortunately, this is not handled by the verification checks that is performed by Bob here. You can read our paper to see how we augment our protocol in order to handle that case. So now let's come to the main issue that we had faced in our protocol. That is, we wanted to give a proof such that we only make hardware, like hardware calls to FHE. That is, we make black box use of FHE and prove that we indeed compute the correct function. So for this, we make use of the information theoretic proof system, that is probabilistic checkable proofs of proximity. So here, Alice holding input X and witness W, it's going to compute an encoding of X and give oracle access to this encoding to Bob. Along with that, it's also going to generate a proof pi for the statement that relation R on input X and W outputs accept, and it gives oracle access to Bob for the proof pi. And then Bob makes at most 2 root Q queries to both the input encoding and the proof pi. And there are PCPP constructions which incur polylog verification overhead. And there are even PCPP constructions in which the prover's computation time is quasi-linear. So now let us see a failed attempt. So in this failed attempt, what Bob does is that it's going to encrypt its input, and then it performs homomorphic evaluation of function f. Then it computes an encoding of x2 and encrypts it under the public key that was delivered to it by Alice. Then it commits to this ciphertext and the output ciphertext and gives it to Alice. Now it considers this relation R, which outputs accept if and only if x1, x2, and y, which have been given as inputs, are such that function f, when evaluated on x1 and x2, outputs y. So now it considers the ciphertext that encrypts Alice's input, that encrypts Bob's input, and the ciphertext that encrypts the output. And under FHE, it's going to compute this PCPP proof. Then it commits to this PCPP proof and it gives it to Alice. Alice then runs the PCPP verifier at its end. And for input queries can easily be handled because it has its own ciphertext, and it has received ciphertext of the encoding of Bob's input and the ciphertext of output. And in order to handle queries for the proof system, it will simply request Bob to open ciphertext at location I of the proof pi that the PCPP verifier had requested for. And it's going to verify, first decrypt and verify that it opens correctly. And it repeats this process for all bits I that PCPP verifier had requested. Unfortunately, this approach is of course not secure because you give ciphertext E, ciphertext that encodes Bob's input in the clear, and information about Bob's input is also leaked in the PCPP proof. So in some way, we need to use a trick similar to how we handled Alice's input. That is, we need to generate VSS secret shares of the encoding and the PCPP proof. But then we need to somehow have a way to verify this without leaking any information to Bob about the underlying input and be assured that this proof is still robust against malicious Bob. So now, as we discussed, we generate VSS secret shares under FHE of the encoding and the PCPP proof. And then we commit to this shares and give it to Bob, give it to Alice. Now notice that the commitments for the PCPP proofs, we make use of vector commitments because we want a succinct communication protocol. So now the idea to effectively prove Alice that the computation has been done correctly is to run the PCPP verifier in the MPC in the head approach at Bob's end. So for this, Alice is going to send a randomness R with which the PCPP verifier at Bob's end that is executed in MPC, MPC can be verified by Alice. So once Bob receives this randomness R, under FHE, it's going to execute the PCPP verifier in the MPC in the head approach. Now, all this MPC in the head approach is, of course, executed under FHE. So in the end, you obtain ciphertext of the views of the MPC in the head approach. And for whatever bits that have been accessed in the MPC in the head approach, you make use of the corresponding bits that have been encrypted in the proof and the input encoding. Finally, you commit to this vector of ciphertext of views of MPC in the head approach and give it to Alice. Alice then will request for opening a subset of these views, and you are going to give the openings of the encoding corresponding to this subset. And the only thing that we have to be clear about is the opening that we send for the proof pi. Here, we do not send all the bits, openings of all the bits, because then our protocol wouldn't be succinct. We only open those bits which have been actually accessed by the PCPP verifier that was executed in the MPC in the head approach. So after this, Alice performs the following checks. First, it verifies that the commitments have been opened correctly. Then it checks that the VSS shares of the encoding and the PCPP proof and also the MPC views are correct. Then it checks that the MPC views all output 1, that is the relation indeed that is the relation that we started with indeed accepts. So this convinces Alice that Bob had correctly computed the output. So yes, there are several other subtleties which I haven't discussed in the talk, but this is the high-level approach. And as you can see, we compute whatever we compute under FHE is information theoretic, and we never prove any computation of FHE in a black box manner, in a non-black box manner in our protocol. So this way, we get an efficient protocol. And yes, that's it for the talk. Thank you.
Thank you. Do we have questions? No questions? Oh.
For the talk, I might have missed this in the beginning. How do you guarantee the correctness of the initial ciphertext from Alice? Would it be a chance that it would actually produce an incorrect ciphertext?
Yeah, so there are two things it can do. One thing is that it can encrypt something garbage and send it to Bob. So in that case, that can be handled by the robustness of VSS. But the other issue is that it can give an ill-formed ciphertext. So in order to handle this ill-formed ciphertext, what we do is that we compute a dummy ciphertext that takes all the ciphertext that has been received from Alice, and we kind of create a zero ciphertext. So if there is any ill-formed ciphertext, then this ciphertext would be ill-formed, and the entire computation would be ill-formed. And if it's a correct ciphertext, like if all the ciphertexts are well-formed, then you will indeed have a ciphertext that computes, that has encryption of 0. You simply add that to all the computations under FHE that you had done, so you get to verify.
Thank you. And is there no equivalent to like selective failure attack like you have in garbled circuits?
No, and this
okay.
it doesn't.
Okay, thank you.
Yeah, no.
Any other question?
So I didn't understand the answer. So if opening up the black box a little bit, so Alice generates a key, she encrypts some stuff to Bob. Now, if she uses if she uses valid randomness, but just or maybe just slightly over the border, then the function coming back when she decrypts it will kind of reveal something, won't it? So how do you actually make sure that the randomness
so for
isn't
this,
going to
we
give
make
that
use of
selective failure?
circuit private FHE. So circuit private FHE does not leak any information, and we do not require to make use of the stronger notion of circuit private FHE, a weak circuit private FHE, which reveals the depth and the width of the circuit, it works for us. So circuit private FHE guarantees that no information about the underlying computation gets leaked.
What's that, sorry?
Okay, thank you. I think it's enough. So let's thank the speaker again.
Thank you.
Our next talk will be on simultaneous message and succinct secure computation. The talk will be given by Sasha Servan-Schreiber, and
Thanks a lot. It's my pleasure to present simultaneous message and succinct secure computation. This is a new way of thinking about MPC that has some different, many different applications. For short, we call this SMS secure computation. It's joint work with Alep Boyle, Abhishek Jain, and Akshay Srinivasan. So the setting we consider in this talk is we have two-party secure computation where each party has a private input, and the goal is for them to compute a function f of xy without learning anything else. And so what is kind of the simplest protocol we can dream of for this in this setting? If we take inspiration from the Diffie-Hellman key exchange protocol, the most simple or natural approach would be to have Alice and Bob encode their respective inputs using some kind of encoding function to derive public encodings PEA and PEB that they could then exchange in one simultaneous message. And then after this exchange, maybe there's a decoding function that they can run locally to then derive the function output. Well, this is a very natural way of thinking about it. Unfortunately, it doesn't work because we need at least 2 rounds for secure computation. And the one sentence way of seeing why this is required is because if such a protocol were possible, Alice could just perform a resetting attack by trying to decode with many different x's on her side and then learn more than just the function output f of xy. So this is why 2 rounds are required. However, if we relax this model just a little bit and consider a setting where instead of having the function output decoded, Alice and Bob decode secret shares of the function output, then this doesn't violate the 2-round lower bound because they still need another round to recover the function output. And so this has a very nice property, which is that it's almost exactly what I described before, except now they just obtain secret shares that can be added together to recover the function output. The thing is that they don't even have to interact on the second round. They can just post these shares to a bulletin board and have anyone reconstruct at the end. There are currently 2 ways to construct a protocol that has this form. One is using spooky encryption, which we know how to build from LWE or indistinguishability obfuscation. And if you were at the talk on Monday on multi-key homomorphic secret sharing, we can do this from DCR. But the question we ask for SMS is, can we actually push this model even further? And so what do I mean by this is, instead of having Alice and Bob have equal-sized inputs, what if Alice has a very big input, like a database, and Bob has a small input, like a query? If we just ignore security for a second and just think of what the simplest protocol is for this problem, of course it's having Bob just send the short input to Alice, have Alice compute the function herself, give it on her big input, and then just send the output back to Bob. This achieves optimal communication for Bob because Bob just has to send his input, but Alice learns Bob's input, which makes this protocol insecure. So the question we ask in the paper is, can we get a fully succinct protocol that has the same communication pattern I described for the insecure version, where the public encodings do not grow with the size of Alice's big input X. So what I mean by this is now Alice will just encode, Alice and Bob will encode their inputs as before, but this public encoding is both succinct in the Alice's input X and the function output f of xy. So even if you have a very long function output, it stays succinct. And so I call this input and output succinctness. And it turns out this is kind of a way of thinking, if you're familiar with trapdoor hash functions, this is a way of thinking about, it implies trapdoor hash functions, and it provides a simpler way of describing that primitive. So what do we know about constructing SMS using the syntax I described before? Well, we know from a recent work from last year that we can get SMS for vector OLE functions. So these are fairly simple functions. And in this work, we show that we can build SMS for all functions from LWE, which get both input and output succinctness, as well as function succinctness, which you would want for, or succinctness in a circuit description. And we also show that from indistinguishability obfuscation and SSB hashing, we can get SMS for batch functions. And there's a concurrent work at Stock this year that focuses on the trapdoor hash function case, and achieves near optimal parameters, so improving the parameters in our work a little bit. Okay, so what are the applications of SMS, and why is this an exciting primitive? But I hope you see why I like it so much. Turns out that we show that SMS can be used to construct trapdoor hash functions for all functions. And before SMS, the only way we knew how to do this, the only functions that we knew how to build trapdoor hash functions for were for linear functions. So this significantly increases the predicate descriptions possible for trapdoor hashing. We also show that SMS can be used to build a generic compiler for obtaining correlation intractable hash functions from LWE. We show that SMS from I/O can be used to construct succinct secure computation with very long outputs, which is an alternative to the protocol of Hubacek and Wix. And we show that SMS can be used to build rate 1 FHE from any FHE scheme through a generic compiler once again. So hopefully you see why this is a useful primitive that connects many different areas of both crypto and MPC. And so now I'll just describe how we build SMS from LWE. We're going to require 2 ingredients for this. The first is an FHE scheme with a nice decryption property. So the only thing we need from this FHE scheme is that it has this near linear decryption, which means that if we take the inner product between the ciphertext and the secret key, we obtain a noisy decryption of the ciphertext. And the second ingredient we'll need is GVW evaluation algorithms, which we'll use as a black box. This is eval-PK and eval-CT. I don't have time to go through the syntax, but for those of you who are familiar with this, we just use them as a black box. Okay, and I'm going to describe how we get SMS for single bit outputs. Getting SMS for that's output succinct can be done with a bootstrapping technique that I'll briefly allude to at the end. So the main idea is we're going to have Alice somehow hash her input into this public encoding that she will send to Bob. And Bob, on his end, will encrypt his input Y with an FHE secret key, which I'll denote as the black key here. And then he will encrypt the FHE key with a different key to derive this ciphertext CT. And this will be his encoding that he sends to Alice. Alice will use this information provided by Bob to compute an evaluated ciphertext CT hat, which I'll explain later. And then there will be some magic procedure that will use the encrypted FHE secret key to decrypt this evaluated ciphertext into a secret share. Okay, so mapping the ingredients I had before to this high-level intuition, we're going to use the eval-pk algorithm from the GVW predicate encryption scheme to hash the Alice's input X. And then we're going to, the evaluation algorithm will be mapped to this eval-CT algorithm. And then we're going to use the near-linear decryption property to derive the secret share. That's kind of the magic trick at the end. Okay, so in more detail, if we look at if we just consider a function f that has a big input and a small input and outputs a single bit, the way Alice, what Alice is going to do in the SMS protocol is first define a circuit C that is just going to take as input, the circuit takes as input an FHE ciphertext CT, which is not defined yet, and then compute the FHE evaluation algorithm for the function f using her input X and the input ciphertext CT. So the circuit C has X hard-coded in it. And using the circuit C, she will derive a commitment to the circuit using the eval-pk algorithm. This will be her public encoding that she sends to Bob. And the thing to note here is that it is a polynomial in the depth of the circuit C and the security parameter, and so it's independent of Alice's input length, X. Bob, on the other hand, will generate a FHE secret key SK, compute the encryption of his input Y using the secret key SK, generate a second key, so this is the white key in the high-level intuition slide, that has, so this will just be a standard key with 1 in the first coordinate, and he will encrypt under the second key the ciphertext, the FHE ciphertext, coordinate by coordinate. And likewise, he will encrypt the coordinates of the FHE secret key under this orange key S. So the way to see this is that the UIs are going to be nested encryptions of his input Y under the 2 keys, and then the VIs are just encryptions of the coordinates of the FHE secret key. And again, here, this only grows with Bob's input length Y, or the length of Y, and is independent of X. So far, we've achieved the input succinctness requirement. Now, given this information from Bob, Alice will first compute this eval-CT algorithm, which takes as input all this information that was provided by Bob. And if we just look at the first coordinate of the evaluated ciphertext, and you have to believe me that this is actually what the correctness syntax of the eval-CT algorithm, we will obtain the circuit C evaluated on CT with the inner product of the secret key SK, the FHE secret key SK. And all of this will be encrypted under the orange key S. And because Bob defined the first coordinate of the secret key S to be 1, we simply get an encryption of the inner product of CT and SK. Because of how Alice defined C to be the FHE evaluation algorithm of the function f, this is just the FHE evaluation on input X and CT. And by correctness of FHE, that's just an encryption under the secret key, FHE secret key SK of f of X and f of XY. And finally, by the near linear decryption property of FHE, we obtain the function, an encryption under the secret key, the orange secret key S, of the function f of xy evaluation. Cool. So if Alice just defines this as her share of the output, Bob, who has the secret key S, that he computed earlier, and is given A sub c by Alice, can compute the corresponding share S transpose A sub c, and if you add these two together, the result will be a noisy function evaluation. So we almost got what we want, except that we wanted the shares to combine to the function output rather than this noisy function output. However, we can use a very simple trick, which is rounding of noisy secretures. So if you have secretures that are noisy in that way, you can locally round them, provided you set the LW parameters correctly. And this means that if Alice and Bob just round their respective shares, they will obtain additive shares of the output. And so this is how we get the additive sharing. And so this was for single bit outputs. How do we get long outputs? I don't have time to explain that in this talk, but the idea is we use SMS for vector OLE to perform this decryption step at the end in a succinct manner. That's it. Happy to take questions.
So we have plenty of time for questions. There's no question, so let's thank the speaker again. Can I? Okay. So our next talk will be on efficient distributed randomness generation from minimal assumptions, and the talk will be given by Elisaveta Masserova.
Okay, yeah, hi everyone, I'm Lisa, and this is a joint work with my amazing co-authors, Chenda, Joao, Pratik, and Aravind. And to start things off, let us briefly recall why we need randomness in the first place. And the answer is that randomness is truly used everywhere, from its usage in blockchain applications to more traditional settings, such as to ensure fairness during the green card lottery, and its usage in clinical trials and financial audits. And what is common for all of these applications is that we would like to have randomness that satisfies a few important properties. First of all, we would like to have randomness that is hard to predict. We would like to ensure that no one can bias the randomness. And finally, a lot of the applications profit from randomness that can be seen by everyone. And this is exactly what we provide in this work. And to get such randomness, we will be working in the PASO model. PASO stands for Parties Speak Sequentially Once. And it is a model that has been proposed at Crypto 2022 by Nielsen, Ribeiro, and Obrimsky. And a turn in this model has been inspired by YOSO, You Only Speak Once, which was proposed by Gendry et al. Okay, so as the name says, in PASO we will have parties that will be speaking sequentially. So parties P1 up to Pn speaking one after another. Each of these parties has its local source of randomness. And finally, what each party can do is each party can simply publish a message to the broadcast channel. And additionally, a party can also send private messages to future parties. So sending messages backward is not allowed. The adversary can corrupt up to T out of these N parties. Okay, and depending sort of on how the message forwarding is done, we will be distinguishing between two variants of this model. So let's say that a party PI wishes to send a message to an adversarial party PJ. In the execution leaks variant of PASO, the adversary will see the message M only when PJ is being executed. And in the standing leaks model, the adversary will see the message M as soon as PI sends it. Okay, and in both of these sort of variants, our goal will be to generate an unbiased public random bit from the public messages that were published by P1 up to Pn. There has been already some prior results. So specifically, in the original work that introduced this model, the authors proposed some information theoretic protocols. But unfortunately, the problem with these protocols is that they had exponential communication and computation complexity. And so to sort of improve the situation, a few years ago, my co-authors and I had an FC paper which switched to the computational model and introduced the first polytime protocols. The first of these was based on publicly verifiable secret sharing. This protocol was efficient, but unfortunately required setup. And the second one was based on verifiable secret sharing, so this time no setup. And it required 5T plus 4 parties in the sending leaks model and 4T plus 4 parties in the execution leaks model. And these two results were very nice, I guess. But the problem was that we still felt like we don't have a full understanding of what is possible in computational PASO. And so this is exactly what we wanted to explore in this work. So we wanted to sort of figure out what is the actual landscape of computational PASO, what is possible in terms of resiliency, and maybe what are some lower bounds. And to make things interesting, we will be working in the plane model. Okay, so these are some previous results. So we had the information theoretic protocol by Nielsen, Ibero, and Dabrimsky, and the DDH protocol, which was from our last FC paper. Okay, and so in this in this paper, we introduced a few protocols based on different assumptions. So our first one was based on, one-way functions. Then we provided some variants which are based on non-interactive commitments. These have different trade-offs in terms of resilience, as you can see. And also the first non-interactive commitment-based one is polytime for any T, but the second one is actually only polytime for T from O of log lambda. And finally, we also provide an impossibility result, which shows that it is impossible to have computational PASO in the sending leaks model for less than 3T plus 1 parties. And we have the variants of these protocols also in the execution leaks model. They are pretty similar, but we can sort of slash T parties in each case. What is interesting, though, is that in the execution leaks model, the impossibility results are slightly different. So here we were actually only able to prove impossibility for 2 very specific cases, and you will see later in the talk why this was the case. Okay, and so for the purpose of this talk, I will focus on one protocol, the one on non-interactive commitments, and on the impossibility result. But before we go there, let's maybe think what are sort of some very naive ways of obtaining PASO protocols. And the first thing that comes to mind is that you can probably linearize any sort of traditional round-based stateful protocol. What I mean by this is, well, let's say that we have 3 parties, P1 up to P3, in a stateful protocol. Then what we can do is we can simply take these parties and have them speak in sequence and execute the first round of the stateful protocol, but now in the PASO model, right? So they will be speaking one after another. Then we can add the same amount of parties to execute the second round, and the same to sort of perform any final computations and produce the output. Okay, and what do we do with the messages? Let's say that in the stateful protocol, P1 sends a message to a party P2 in the first round. Well, in the parser model, we can send the same message from the party P1 that is sort of emulating P1's first round to the party that is emulating P2's second round. And to pass a state, let's say that P1 actually has some state that has passed between the first two rounds, we can simply do the same thing. So like we can simply send a private message from P1 for the first round to P1 for the second round. And same with all the other messages that we have. So this is nice, but the problem with this is that it actually has bad resiliency, right? So like we still can only tolerate T corruptions, but now instead of n parties, we actually have n times r+1 parties, where r is the number of rounds in the stateful protocol, stateful round-based protocol. Okay, so can we somehow improve the resiliency? And the second somewhat naive thing is to sort of use the quite famous commit and reveal paradigm. And how it works in the parser setting? Well, we will have T+1 dealers and 2 T+1 receivers. And what each dealer will do is each dealer will simply sample a random coin and commit to this random coin by publishing it on the broadcast channel. And each dealer will also send an opening to each receiver. So all the dealers do exactly the same. And then what each receiver will do is each receiver will simply publish all the sort of correct openings to the commitments that they received. And let's say that we want to count the dealer's value if the majority of the receivers reveal a correct opening. So the intuition being that, okay, the majority of the receivers will be honest, right? So if the dealer was honest, then they can probably simply publish the values that they received, right? And so this will ensure that the dealer's value can be reconstructed for an honest dealer. And the final result will be the XOR of all the RIs which come from the valid dealers. And since at least one of the dealers was actually honest, the final XOR should be good enough as a randomness right. And unfortunately, this intuition is incorrect. Why? Well, because it's actually very easy to perform an attack if you can corrupt one dealer and one receiver. So for example, let's say that in this case, D3 and R5 are corrupt. What D3 can do is D3 can simply commit to bit 1 and send opening to half of the honest parties. Now what the R5 will do is R5 will sort of see all the information. So in particular, R5 also knows what values were published by D1 and D2. And it can decide based on this whether to open R5's commitment or not. And so this way, D3 plus R5 can choose whether to flip or not to flip the result by sort of aborting D3's contribution if needed. And so like we need to somehow find a way to prevent this kind of conditional abort attack. And there are different ways to do this, but for now let's focus on the one that we chose for this non-interactive commitment-based approach. Okay, so we will actually follow this paradigm. So we will again sort of compute randomness by using an XOR of a bunch of values Ri, where at least one Ri will be honest and unpredictable before reconstruction. But now we will ensure that all the adversarial RIs are actually fixed before the reconstruction. And to do so, we will rely on something that, for the purpose of this talk, I will call a weak distributed commitment. Okay, the protocol for the weak distributed commitment is actually quite simple, so I will first introduce the protocol, and then we can talk about the properties that we achieve. Okay, so this will be in the execution leaks model for simplicity, the first thing is that in the weak distributed commitment, the protocol is parameterized by the set S. For this example, let's say that set S contains parties P1, P2, and P4. Okay, so to commit, the dealer will publish a simple non-interactive commitment and send the opening of this commitment to exactly the parties in S. Parties in S can then complain if needed. So if they did not receive the opening from the dealer, or if the opening is incorrect, they can complain. And otherwise, if they are happy, they can send this opening to the parties in the set R, so to every receiver. Then the receivers can simply publish the values that they receive. And to reconstruct, you basically take any sort of valid opening that was published by the receiver. However, if any one of the parties in S complains, then we simply abort the whole thing. So then no value will be reconstructed. Okay, so this protocol actually satisfies a few nice properties. So if everyone in S was honest, then we know that the honest dealer's value will be hidden prior to reconstruction. And also we know that an honest dealer's value will be reconstructed. Why? Because everyone in S will simply forward to the receivers, right? And they will later publish, at least one receiver will later publish the correct thing. Additionally, if at least one PI in S is honest, we know that PI will check this opening. And so if PI did not receive a valid opening, then everyone will abort because PI will complain. And otherwise, PI is happy, so PI will send this valid opening again to the reconstructors. And so this achieves that even if the dealer is dishonest, the dealer only has a chance to sort of abort the computation during the sharing phase, and this will be seen by everyone, and so everyone will know that they should not take the value of this dealer. Okay, so the value is actually now fixed during the sharing procedure. Okay, what can we do with this? Well, we will have a bunch of dealers, again, T+1 dealers as in the naive protocol. However, instead of sort of doing the commitment to only a single value, they will use this weak commitment and commit to a bunch of different sets S. And each such commitment will produce a sort of one partial value Rij. And then we can sort of sum all the contributions by all the dealers that survived the commitment phase. Okay, so what do we want though? We want to have one honest dealer, right, to ensure that at least one value was actually coming from an honest party. This is ensured because we simply take T+1 dealers. And we also want to have that sort of this dealer has at least one fully honest set Sij to which it commits, right? Because this will ensure that this value Rij is actually hidden during the sharing phase and later will be reconstructed. And additionally, we want to have that every such set Sij has at least one honest party to ensure that we commit also the dishonest dealers. And there's fortunately a very easy way to do so, namely we can have each dealer share towards every subset of size T+1 of a single set of size 2T+1. Why this works is, well, as you can see for the last property, right, we want that every set Sij has at least one honest party. This is ensured because all the T+1 subsets do have at least one honest party. And finally, we also ensure that the honest dealers have at least one fully honest set S to which they're sharing. This is ensured because if you take this set of size 2T+1, it can contain only up to T dishonest parties, right? And so T+1 guys in this set will actually be honest. And so this is how we ensure that there is at least one subset of size T+1 that is honest. Okay, so the resilience of this protocol is 4 T parties in the sending leaks model, and it also needs 3 T+1 parties in the execution leaks model. Okay, and for the final result, let's briefly talk about the impossibility. And here let's focus on the interesting case, which is sort of 1 corruption and 3 parties. Okay, so consider party P3. There are actually 2 choices for this party. Either the party P3 can sort of change the output of the protocol by aborting, in which case it would be able to bias. So this is not what we want to do. Or basically P3 sort of aborting the protocol should not change the honest coin by too much. Okay, so what is happening in this case? In this case, the coin is actually determined by the public values of P1 and P2, except for some negligible probability. Okay, that's good. But now what happens to P2? Now P2 actually knows that it can emulate the honest coin by simply considering P3 that aborts the protocol. And so either 2 honest executions of P2 can lead to 2 different coins, and P2 can predict the outcome by simply thinking that P3 outputs bottom. In this case, P2 can again bias. Or basically, the honest coin is fully determined by P1. This is obviously also not good, because then the adversary can simply corrupt P1. Okay, so the interesting question is, can we generalize this intuition? And the answer is that it actually depends on whether we are in sending leaks or in the execution leaks model. So in the sending leaks model, the adversary will receive the value exactly after it was sent to a corrupt recipient. And here we can actually generalize. So by simply applying the same argument to blocks of size t. And the execution leaks model, where the adversary receives the value only after the party is being executed, the answer is actually not clear, because we cannot really sort of hope to do the same arguments to blocks of size t, because maybe a block of size t can bias, but maybe only if the adversary knows messages that are being sent to every single party in this block. And this will potentially happen too late. So it's not fully clear how to do the same argument. And so we use a trailer technique to prove this for the specific case of 2 corruptions and 6 parties. Okay, so this is pretty much all that I had. There are lots of interesting questions in this model, so we can think about further optimizing the role complexity, since there are some gaps between sort of our lower bounds and the constructions that we have. We can also think about optimizing the communication and computation, and we can think about obtaining different passive primitives, for example, of obtaining full-blown multi-party computation. Okay, thank you so much.
So do we have questions? There seems to be no questions, so let's thank the speaker again. And let's thank all the speakers of the session again, please.